I know what a barrel of fun 1D kinematics was, so we're going to slap another dimension into the mix. 2D kinematics it is. Before we do so, we need to be well versed in a tool that is vital to the study of 2D kinematics, and that is vectors. So we're going to do a little review of vectors, a little bit of new stuff. Let's get started. On the screen you see the definition of a vector. A vector is a general term for any quantity that has both a magnitude and direction. For example, a force, right, which we would express in the following way: 5 newtons west, for example. Whenever there's a push or a pull, there's a direction involved, right? You can't talk about force without talking about direction. Displacement is similar, right? Perhaps negative 8 meters, right? Remember, displacement is motion in a given direction, right? The straight line distance between 2 points in a given direction. 80 meters per second south. Okay, another example of a vector quantity. Notice that every vector has both a magnitude, right, the size or amount, and a direction. Velocity is special. We come across it so often that we give its magnitude its own name. Do you know it? Indeed you do. The magnitude of velocity is called speed. Okay, in 2 dimensions, right, when you jump out of 1 dimension and you forget just up or down or just right or left or just north or south, you can no longer use positive and negative because the number of possibilities opens up exponentially. You're going to have a vector that can be anywhere in the xy plane, right? So we're going to be using angles primarily to determine the direction of a vector. You see here that it's often useful to work in what's called vector components. A component is simply the projection of that vector on a given line. Imagine shining a light down. Let me change the color here. Imagine shining a light down vertically like this, right? Imagine the shadow that that white arrow would cast on a horizontal line. It would make exactly this shadow right here, correct? You can also think of the components as an alternate way of getting to the same place, right? So if vector A were a displacement, right, from this point to this point, well, you could get there alternately by going right and then up. There are 3 primary ways to determine the vector direction, okay, if you're working in 2 dimensions. One is to use the cardinal directions, right? And by cardinal, I mean, okay, east-west. So typically on a piece of paper, right, your cardinal directions are going to look like this. Here I've just made a random vector, a displacement vector of 5 meters at 37 degrees here. Okay, that's the angle there it makes with the x-axis. And I went ahead and sketched in the components already, right? Conveniently, I chose a 3, 4, 5 triangle. So in cardinal direction terms, you would say that this was 5 meters at 37 degrees north of east, right? I use east as my reference line, 37 degrees north. I could also alternately, right, I could use this one here, okay, its complement, right, that would be 53 degrees east of north, right? Either of those is valid. That's called using the cardinal directions. Also, I could use the polar directions, okay, polar coordinates. In order to do that, I would need to change these. I no longer use north, south, east, west, but instead I start on the far right, which is called the positive x-axis, right, 0 degrees, and I go counterclockwise, okay, I go counterclockwise around the circle and determine the direction that way, right, so 90, 180, 270. So in polar coordinates terms, this vector would be 5 meters at 37 degrees, right? No direction involved. Now, if you wanted to be tricky, you could actually go clockwise and use negative angles, okay? And this would be 360 minus 37, right? That's negative 323. That's pretty awkward for this particular vector since it's in the first quadrant. So you would never do that. But if our vector were in the 3rd or 4th quadrant, it's more likely that you would use negative degrees. Finally, you could do what's called the unit vector, okay? And this may be new to you, at least in physics, hopefully not in math. Hopefully in math you've seen it before. You could simply specify the vector. Instead of using an angle, you could use the components. So we would write it like this: A equals 4I, right? 4 meters in the x direction, I being the unit x vector, plus 3j. right? First quadrant stuff. So 3 ways to specify the magnitude and direction of a vector. Let's go to the next screen, which talks about vector operations, okay? When you add vectors, you generally do what's called the tail to head method. In other words, if you want to know, where would I end up if I walk this way and then I walk this way, right? That would be a vector addition problem. So all I have to do is arrange the vectors head to tail, right? So I'm going to do that now. Oh, that would not be it. I'm going to just move this over here. I'm going to put them head to tail, okay, like so. And then what I'm going to do is I'm going to draw a new vector, right, from the beginning to the end, which looks like this. And that represents my resultant, right? Let me do that in a different color. This here represents my resultant, right? That's the result, okay? Now, I don't have a simple math way of getting that answer, but that's how I do it on paper anyway, right? So that's called the graphical resultant using the tail to head method. When you add vectors, okay, if you look down below here, they typically come in 3 varieties. I'm going to use Mr. Atman's terminology here. The first one you see is very friendly vectors, okay? When they're in a straight line, they're very friendly. You just add a plus b, okay? So you're going to get, in this case here, you're just going to get one long vector, right? The second variety is when they're opposite each other, okay? That's going to be a minus b, right? A plus b in the opposite direction is the same as a minus b. So in this case, you're going to get one short vector like that, right? But the point is you subtract the magnitudes, right? And they're very, very friendly. You add the magnitudes. When they're very friendly, you subtract the magnitudes. And then finally here, the third example you can see, if I have them orthogonally arranged, right? Orthogonal being perpendicular. Oops, let me redraw that. Then you also know how to find that numerically, and that is simply Pythagging, in case you didn't know that technical term, right? So you have 3 options when adding vectors. You are going to either add the magnitudes, subtract the magnitudes, or Pythag the magnitudes. In addition to vector addition, you can also perform vector subtraction, okay? And here I've got a minus b, okay? In the case of a minus b, that is simply going to look like this here. Let me kind of recreate it down here. It's going to look the same as a plus negative b. And negative b is simply the exact same component, excuse me, the exact same vector, but the opposite way. So if this one here is b, right, then I've just drawn negative b, okay? So that's negative b, and I'm just going to take negative b, right, and I'm going to move it to the end of a, like that. So that right there would be a plus negative b, okay, a plus negative b, which is the same as a minus b, and I would have this as my resultant, right? My resultant would be that way. So that's how you subtract vectors. You just add their negatives. Finally, vector multiplication. The only vector multiplication we're going to deal with now is when you take a vector a and you multiply it by a scalar. Right, so here, if this is a, if this is vector a here, right, then 2a is simply going to be the same vector with twice the magnitude, right? So it's going to look like something like that, right? That would be 2a. And I think pretty obviously you'll see that negative 2a, right, if you multiply by a negative, it's just going to flip the direction around. Vector multiplication does come in 2 other varieties, cross products and dot products, but we're going to cover those later in the course. Let's look at another example of vector addition. This would be a kind we haven't covered yet. This would be called unfriendly vectors, right? Because if you look at these vectors here, a and b, I went ahead and arranged them head to tail already. But if you want to add these vectorially, okay, the resultant is going to look like this right here. Okay, so the resultant is going to be like that. But the problem is those vectors are neither very, very friendly, right? They're not in a straight line. They're also not very friendly. In other words, they're not opposite. And they're not even friendly. They're not even at right angles. So when that's the case, you're going to have to resort to trig, okay? And that means taking a vector, a 2D vector, and replacing it by 2 1D components, right? Where the 1D is the x and the y. So I'm going to pause. I'm going to sketch in the components, and then we'll see how to proceed. All right, I added a lot of material, so it might take you a second to make sense of it. But I added in the angles, right? So vector A is at angle theta, okay? and angle B is at angle phi. So if you remember, using sines and cosines, right, SOHCAHTOA, the components would be the cosines and the sines. Now, what I'm after, let's, all this information, let's not forget what I'm after. What I'm after is the magnitude and the direction of that resultant. Okay? Now, do you see that once you've broken the vectors into components, you want to group all the horizontal vectors together, add them up, group all the vertical vectors together, and add them up. I'm going to draw that to the right now. Okay, you see on the right I've assembled the two. Now look what happens here. Notice, by the way, I changed the resultant to the color red so there wouldn't be confusion with the x components. But notice what I get here. I get now a right triangle, and that's a that's a friendly vector, right? I can Pythag the components to get the resultant, okay? And then also very important, I can come in here. This will be a new angle too, right? Because notice back over here in the original drawing, this angle is not equal to phi or theta. It's some new angle called alpha, okay? I can get its direction too by doing the inverse tan function, right? So that would look like this, inverse tan, opposite over adjacent. So the sum of the y components over the sum of the x components, right? Like that. Where this would be, let me write all this out. I'll pause and write it out so it looks nice and clean. Okay, I wrote it all out a little more nicely here using the terms yt and xt for x total and y total. Right, so the resultant is going to be Pythagorean theorem, and then the angle would be the inverse tan of the two components, right, using SOHCAHTOA. So that's called adding vectors by components. And that's what you would do with unfriendly vectors, right? Vectors that are neither in a straight line, opposite each other, or perpendicular to each other. You'd have to use this method. Now there was one last method to use here, and that's if you could also add unfriendly vectors this way, and that's if the vectors come in the unit vector variety. Then the math actually gets a lot easier, so you kind of see the usefulness of unit vectors here. Let me show you on the next screen. Again, I've just drawn two random vectors, a plus b, okay, but what I'm going to do now is instead of representing these in terms of like a particular angle, I'm going to write them out in terms of their components. So what you might think about is what quadrant is each of these vectors in, okay? That's right, A is in quadrant 1 and B is in quadrant 4. So watch, I'm going to sketch the components first of all for these vectors in each of those quadrants, and then you'll see how I write those vectors in unit vector notation. Okay, I've sketched them in, and now I'm just going to make some numbers up that kind of correlate to the size, right? So the way I could specify vector A here would be something like this. A equals maybe like 5i, right? It goes in the, and then plus maybe 2j, right? Because it's not as tall as it is long. Whereas vector B is going to look something like this. It's going to look like maybe, I guess, I'll do 2j as well. That's a little bit shorter. Now watch here, minus 8j, right? Because it really goes down. Now, if I want to look at what the answer is going to look like of A plus B, I would have to employ the head to tail method. So watch me do that here. I'm just actually going to drag the vector over here, like so. And then I'm going to take this one and put it head to tail, right? So that now I get a visualization of what the resultant would be of adding those two together. And I'm going to choose a different color. And you can see that my resultant is going to be in the fourth quadrant. Okay, but watch what you do here. Instead of doing all those sines and cosines to get the answer of this resultant in the fourth quadrant, right? You can simply add the components. Okay, so in this case, A plus B is going to look like this. Okay, adding A plus B is going to look like this. You're just going to add by components. So you take the first one, 5 plus 2, I. And then the second component, or excuse me, the j components would be 2 minus 8j, right? So it's really easy, and what you get here is 7i, right, minus 6j. Let's look at the drawing and see if that makes sense. Let's visualize the x and y component of the resultant. I'll pause and draw those in. Wow, I feel pretty dumb. I just now discovered at the end of the vodcast that I actually have an dotted arrow tool How cool for me. Anyway, now the drawing looks nicer. But look at the y component, right? I didn't draw it to scale here, right? I just kind of drew it freehand. But you can see it's, right, that says that's -6 and this is 7. So it comes out pretty well. So when you're given the vectors in unit vector form, adding the vectors together to get the resultant in its unit vector form is a lot easier than doing a bunch of sines and cosines. So that just shows you the usefulness of the unit vector approach to vectors.